All right, today we're unpacking one of the biggest ambitions in all of tech, how Intel plans to build a million-qubit quantum computer. And their strategy is fascinating. They want to stop treating quantum computing like a delicate physics experiment and start treating it like a massive industrial manufacturing problem.
Because this right here, this is the question that keeps quantum engineers awake at night. You see, it's not just about creating a million qubits. The real gut-wrenching challenge is how you individually connect to them, control them, and read information from them, all without the whole system just collapsing into chaos. And that chaos has a name: the wiring nightmare. Seriously, just picture it. Try to imagine running a million individual microscopic wires from your room temperature control electronics deep into a super freezer that's colder than the vacuum of space. Every single one of those wires introduces heat and electrical noise, which is absolute poison to the fragile quantum states of the qubits. You hit a wall where it becomes physically impossible. So this shows you, getting to a million qubits isn't just a numbers game. It's a massive industrial-scale integration challenge. It's about building a coherent, working system, not just a one-off, fragile setup in a lab.
And this is where Intel's big bet comes into play. They're essentially betting the farm that the 50-plus years of experience they have cramming billions and billions of transistors onto tiny silicon chips can be repurposed to solve this quantum scaling problem. They want to take quantum computing out of the cleanroom lab and put it onto the factory floor.
At the very heart of their whole approach is this thing, the silicon spin qubit. The idea is actually kind of elegant. You trap a single electron in a tiny, nanometer-scale cage made of silicon. They call it a quantum dot. The electron's spin, which can be either up or down, represents your quantum bit of information. And the most important part? This whole structure is incredibly similar to the transistors that power pretty much everything in our lives.
And that similarity leads to a really mind-blowing advantage in size. I mean, just look at this. While some other very popular approaches, like superconducting qubits, are measured in millimeters, big enough to almost see, Intel's silicon spin qubits are measured in nanometers. We're talking about a completely different universe of scale.
So what does that get you? How about this? A theoretical density that is 1 million times higher. That's what the size difference means. You could, in theory, pack a million of these silicon spin qubits into the same area that one of some competing qubits would take up. That density, that is the secret sauce for ever reaching a million-qubit chip.
So, how are they actually doing it? Well, Intel's strategy stands on three main pillars. The very first one is all about using their massive factories to mass-produce qubits that are practically perfect and identical every single time. And this chart just lays out the difference plain as day. Instead of the small, handcrafted wafers you'd see in a university lab, Intel is using their standard 300mm production line. I mean, look at these numbers. That lets them produce over 24,000 potential qubit devices on a single wafer with a yield rate of around 95%. Compare that to a lab where you'd be thrilled to get a few hundred devices and the yield would be totally unpredictable. This is the raw power of industrialization.
And they're using their absolute best, most advanced tools, like EUV lithography, to get insane precision. They also build these qubits on a special, ultra-pure version of silicon to create a magnetically quiet little neighborhood that protects the delicate quantum information. And the result of all this, which we saw in their Tunnel Falls research chip, is a 99.9% single qubit fidelity. That number is a huge deal. It's the critical benchmark you have to hit to even begin talking about useful error correction. Okay, so they can manufacture millions of high-quality qubits, fantastic. But what about that wiring nightmare we were just talking about? Well, that brings us right to pillar 2, bringing the control system down into the freezer with the qubits. Intel's solution here is just so clever. It's a two-stage system. First, you have a chip called Horse Ridge 2. It operates at a balmy 4 Kelvin, while balmy for a quantum computer. Think of it as a middle manager, taking all the complex signals from the outside and funneling them down to control big groups of qubits through just a single wire. Then, right down there next to the qubits in the coldest part of the fridge, you have Pandotree. This chip provides the final, delicate, low-power control signals. You've effectively solved the wiring nightmare by getting rid of thousands of individual wires.
And the secret ingredient that makes this all work is something called cryo-CMOS. These are custom-designed transistors built on decades of Intel's research that are specifically made to operate perfectly in the extreme cold, just fractions of a degree above absolute zero. It's a massive engineering achievement that directly attacks that wiring bottleneck head-on. So we have the qubits and we have the control system. The final piece of this huge puzzle is actually telling the machine what to do, and that's Pillar 3, the software. It's called the Intel Quantum Software Development Kit, or SDK for short.
The whole point here is to make this stuff accessible. The SDK uses a C++ interface, which is a language millions of developers already know. And it has a powerful compiler that does all the heavy lifting, translating that familiar code into the weird, complex instructions that qubits actually understand. It's also built for a future where quantum and classical computers are working together, hand in hand. And it even comes with a simulator so you can test things out on their specific hardware. So, you see, when you put these three pillars together, the factory-made qubits, the cryogenic control chips, and the robust software, you don't just have a collection of cool experiments anymore. You have a clear, deliberate roadmap. This is a plan to get to a commercially viable quantum computer.
And we can literally watch them check off the milestones. In 2023, they released tunnel falls to researchers. In 2024, they showed off that Pando tree control chip. The next big step, coming in 2025, is integrating all this with their most advanced 18A manufacturing process. That's what will set the stage for systems with thousands of qubits by the late 2020s, and then the million-qubit era. And this is where the synergy between their businesses gets so powerful. New technologies like RibbonFET, which is a whole new kind of transistor, will allow them to have way more precise control over each qubit. And another tech called PowerVia, which moves power lines to the back of the chip, frees up all this precious real estate on the front for more qubits and more connections. It's incredible. The advancements for your next laptop are literally paving the way for quantum computers.
So why does all of this matter? Why go to all this trouble? Because a machine on this scale could tackle problems that are just completely impossible for even the biggest supercomputers we have today. We're talking about designing new materials for better batteries, discovering life-saving drugs in a fraction of the time, optimizing mind-bogglingly complex financial markets, and creating climate models that are so good they could help us save the world.
Ultimately, what Intel's strategy really represents is a fundamental shift in perspective. It's about taking this monumental physics challenge and reframing it as a solvable, industrial engineering problem, exactly the kind of problem their giant factories were designed to solve from day one.
For decades, the entire story of computing was about making classical transistors smaller and faster. So the ultimate question now is this: will that exact same industrial engine, the world's most advanced transistor factory, be the key that finally unlocks the revolutionary power of quantum computing?